So my name is Joseph Wade, and I will be presenting changes at the Great Sand Dunes National Park. So that I took this photo, and where's the laser pointer? Okay, so I took this photo. It's the Great Sand Dunes. It's in Colorado. So I don't know if you've ever been there before, but if you guys haven't, I recommend highly going. It's really, really cool because it formed, they think, from after the glacial activity in the area receded, it left like a lake, and that lake evaporated, and then it left a bunch of sand. So prevailing winds push it towards the mountains, but spring snow melt, so it gets all up there and snows onto the Cat Mountains, because they reach around 13,000, 14,000 feet, and it melts and brings the snow back down. So you kind of get a cycle going. Where it piles all the sand in this 30 square mile area. And they're the tallest sand dunes in North America at like 750 feet tall. So very, very interesting geology, very, very fun place to go to. Why did I pick the sand dunes? Because it has very, very fast-paced geomorphology. So compared to most geomorphology, you think of like mountains or like things that occur relatively slowly, whereas sand dunes move like 30 feet in 7 years. And they just released LiDAR data in late 2021, which I was previously using LiDAR data from 2014. So I thought, oh, this will be great. I could do some actual like studies and compare the data and see if there's like reasons why sand dunes move the way they do. And so it continued from my previous study, like I said, because I already delved into the Great Sand Dunes, but I thought this would give me more information than I had touched up on before. So this was my previous study where I was trying to identify vegetation, and you can see the sand dunes move from 2015, 2019, they move forward just a little bit, and that's like 10 feet right there, even though it's kind of difficult to tell because I didn't put a scale. But yeah, it moves. So sand dunes move, which is interesting and obvious, but I mean, not extremely obvious. But so my goals were to try to find variables that can explain the changes at the sand dunes. First, I wanted to identify dependent variables. So what is changing, whether it is aspect or like dune movement, if it's moving a certain way, or maybe just simply elevation, so not even including movement, just like a snapshot and say, well, what is affecting it? So then create variables using those two methods. So first, create the dependent variables and explanatory variables, and then test those variables using regressions, and then also test for spatial effects using geographically weighted regressions. Because you want to see if there's spatial reasoning too. So if it's being affected by heading east or west, north or south. So like I said, my 4 dependent variables I used were the digital elevation map in 2021, so a snapshot in time, elevation change, so subtracting 2021's DEM from the 2014 DEM, and then the aspect change and ridges, which I used a special algorithm where I won't go too deep into, but essentially it just identifies what is a ridge on the Great Sand Dunes. So like the high points of the sand. So this is my general like elevation change ratio. You can kind of see the dunes move forward, and this is in meters, so they do increase pretty high. They move forward all northeast towards the mountains, which you can see in the next slide or the one after that. But they leave a little bit of like a footprint behind them because they lose sand as it moves up the side. So explanatory variables though, where there's a lot more of them. So I used all the previous dependent variables, the DEM aspect change, 2014 aspect, mountain interference, which is essentially my own thing to see how many mountains are in the area vicinity, and then distance from 10,000 feet of elevation, and then distance from creeks and distance from parking lots. So these are kind of some of the variables I use. So you can see here's the creeks, here's the parking lots. And then I also said, here's 10,000 feet. And then it goes up to the next one. And depending on how close they are to these, I calculated it out. Oh, there's more mountain interference. Because I thought maybe the mountains would have like a wind effect on the sand dunes. And so maybe the closer you were to them, maybe that would be detected through like a regression. So I came up with I had a problem with how would I create my regression? So I did 2 models and I tested them. So the first one I did was the grid-based OLS. So I created 300 meter by 300 meter grids covering the entire dune field. And then I averaged each square. It'd be like, oh, what right here, this is the elevation change. And I averaged and added up all the values and then divided by the total number of raster cells and said, okay, so this area had this much of a change and this one had this much of a change. And I did try sums, but sums had problems. So I stuck mostly to averages, but this only gives us around 1,000 cells for the whole dune field. So it's computationally easier than the next one. Whereas the next one, I kind of did OMRRC model, which I named that, which is 1 million random raster cells model. Because across the entire thing, I thought, oh, just select random things and see if that is more accurate. And so it gives you 1 million versus 1,000. But I couldn't do obviously all 150 million cells is what I really wanted to do, but obviously my computer couldn't take that. So these points were used to obtain direct values from the rasters instead of averages. So that's important to keep in mind, is that like it's slightly different variables because they're not averages, they're just direct points like represented on the dots. So comparing the 2 of them, you can see that the one on the left, so grid-based, was actually more efficient. So when you look at the R-squared, you can kind of read it as this explains 75% of the dependent variable, all these explanatory variables do. And this one explains 3.4%. So in most cases, this model is more efficient than this model, except for an elevation change being the dependent variable, but this only represents, it says it explains about 12.4% of the explanatory variable. So it's not really that useful, arguably, and so the VIF is me removing values due to variance inflation factor. I didn't want multicollinearity or essentially meaning variables are too similar. So I removed those and I had to remove them in order to have an accurate coefficients. And so these are all coefficients, which essentially say for every meter of elevation change that occurs, 3, I guess that one's a little bit more difficult because of my algorithm, but to understand, but for every meter of elevation change that occurs, you get 0.00014 meters away negatively from a parking lot on average. So kind of difficult to understand. You have to kind of think it through when you're looking at this, but it's all interesting stuff because these are all the significant ones. And then the NS meant they were not statistically significant, didn't have a high enough R-squared value. Which model performed better? Like I said, it was mostly the grid-based, which I personally think that might be because the other one would probably perform better or been more accurate if I had taken into account that sand dunes are not just purely random. They are going to have clustering occurring because they're literally dunes. So you're going to have ridges clustering and then certain parts of the dune cluster in certain areas. So picking a random sample may have added bias that made it more like incorrect than the other model. But at the same time, I'm not entirely sure if that was, yeah. So geographically weighted regressions is the next part I did. GWRs only include data from the grid-based model due to computational limitations. Using 1 million points is very, very, very difficult. For a GWR, it would have taken too long. So I used the grid-based, which was good too, because it was the one that was more accurate. So it just was overall a better choice to use. So you can see here, the GWR for elevation change. So essentially the way you can read this is the coefficient, like I told you, for every a coefficient means 2.88 meters of elevation change per movement, like increase in ridge, like how many ridges there are. So it increases by 2.8. But as you move south, that number increases. So there are more ridges per movement of per elevation change. So it would be labeled as a south facing on my chart, you'll later see. So this is the same type of thing. It's showing that west-southwest change. It increases as you move to the west-southwest for aspect change to directional change versus average elevation change. And the same thing occurs here. This is the negative. So I label that as the direction away from zero, where the coefficient gets stronger. So this would actually be northeast, negative, because the coefficient aspect change changes for the GWR for ridge. So GWR coefficient, the direction, like I said, shows the strongest movement. You look at these, most of them, they're just kind of randomly chaotic. None of them really, I mean, that makes sense, but like, it's difficult to understand because I probably picked too many variables to look at. So you can't fully understand what is happening. But some of them, I had to remove because they had high variance inflation factors. And then these are ones because they're literally just against themselves. And then these were not statistically significant. And then I put little stars next to these because I was essentially saying there was almost no change. Like the mountain interference was so low that even 10 decimal places down, it would show a change in the coefficient on GWR, but it didn't actually appear on the numbers. Like I would have had to increase, I think, the decimal points to like 20 or 30 places. So it's like, it's still statistically significant. There was just no real change occurring. So conclusions, the data was inconclusive. It wasn't exactly accurate enough on some of the models. I personally think my biggest problem was I created too much data. And also I used this data, only LiDAR data really, to create all the data. So I created slopes, aspect change, and elevation from the LiDAR data. But all of my variables and explanatory variables had to be created from that data. So there was inevitably going to be some sort of like correlation between them. So when I saw 75% of the model of these explanatory variables explain the dependent variable, that could be down to the fact that I literally made the variables from them. I subtracted things against each other and did that. So there might have been some bias in there that I couldn't work out. So in the future, if I ever did this again or tried to redo this, I would consider lowering the amount of data down so that I could run a more complex thing, looking at like, instead of the whole dune field, maybe a piece of it, maybe like, so I could have a complete picture. And then maybe I would reconsider combining instantaneous raster data. So like just a snapshot of 2014 with no temporal change with data that changes over 7 years. Because when you combine them and you try to do that, you're suddenly comparing it's like a derivative essentially of something versus not. So it just makes it too complex. So that's probably what I would do in the future, is not do that again. So thank you. I hope you guys enjoyed my presentation, and now I'll take some questions.